Hello everyone. In the last video, we saw first two types of encapsulation techniques used in mobile IP. Those were IP in IP encapsulation and minimal encapsulation. Now in this video, we will see third type of this encapsulation, that is generic routing encapsulation, or abbreviated as GRE. So how GRE is different from first two types? Now the first two types, that is IP in IP and minimal, always uses at least one network layer protocol, which is IP. So IP in IP uses both IP protocols, that is outer packet also contains IP, inner packet also contains IP. Minimal encapsulation uses at least outer as an IP or inner as an IP, but GRE supports other network layer protocols in addition to IP. Okay, so what are the other network layer protocols? For example, the network layer protocols are well known is IP, then there is ICMP, and then there is ARP. These are used for different purposes. Their functioning is different from each other. IP is used for delivering a packet to an appropriate address. ICMP is used for sending out error messages, and ARP is used when we want to know MAC address of particular host. So ICMP for error and ARP for MAC address. Now if you want to send error messages, or if you want to send a packet which will request an MAC address from the host, then first two types are not useful, IP in IP or minimal encapsulation, because they first two types supports only IP type. Now in addition to IP, if we want to use these two protocols, then we can use GRE. So GRE allows the encapsulation of packets of one protocol suite into the payload portion of packet of another protocol suite. Apart from other protocols of a network layer, the other protocol suites are also supported in the GRE. Well-known protocol suite is a TCP IP protocol suite. So if there is any new protocol suite which is followed by a network, then it can be also supported by the GRE. The packet of one protocol suite with the original packet header and data is taken. Now you can see in the diagram, this is similar to the previous two. Original data and header is taken, and a new header called as a GRE header is appended or prepended to that. So here we are adding a new header, that is GRE header. We are not simply adding original header to the outer header. This new header is inserted in between them. Together, the original header and GRE header forms a new data part of the new packet. So original data plus original header plus GRE header, that becomes a new data. So the additional part in GRE is the GRE header. Apart from it, everything else is similar to the first two types. Now GRE header will convert whatever protocol suite header followed by the inner header into the outer type of protocol suite, and that is very essential because though both the packets can be of different protocol suite. Okay, so let's say this is IP, outer header is or outer packet is IP and inner packet is ARP. Then ARP header must be translated into IP header, and that translation is done by the GRE header. Okay, so that is the meaning of this GRE header. Finally, header of the second protocol suite is put in front. Now next one, let's see the actual mechanism of generic routing encapsulation. Now if you see, there are three parts. First part is the outer header. This is outer header. Up to this part, that is in yellow, this is GRE header. So GRE header is in yellow. Now first diagram shows the RFC 1701 update, which is the original version of GRE, and the second is a update to that original version RFC 2784 updated by 2890, which was further updated to 2890. So, and the last part contains the inner header. So this is inner header. So 3 headers and 1 data part followed by payload or data part. Now if you observe, outer header seems to be IP header. So most of the fields are same, or most of the fields are same to the previous two encapsulation types, because it is same IP header where version field indicates IP version 4 or 6, IHL, DS, TOS, all the fields are same. The difference is this field, which is layer 4 protocol field. Now this field indicates type of the protocol used in the data part. Now in the data part, which is this part for the outer header, this is the entire packet. Now for this header, this is a data part. Now in this data part, which type of protocol is used? The GRE is used. That's why here GRE is mentioned. Okay, apart from this, everything else is similar to the previous encapsulation technique, like checksum, source address is IP address of home agent, destination address is care of address, and other fields also. Okay, now this is followed by a GRE header, which is this one. Now GRE header contains several new fields. Let's see these fields one by one. It begins with C, R, K, capital S, small s. These are individual bits which indicate whether these fields exist or not. C stands for checksum. So if C is 1, that means checksum field, which is an optional field, exists in the GRE header. Similar to that, R field, if R field is 1, it indicates that routing field, which is again optional field, it also is present in the GRE header, and so on. For K is equal to 1, it indicates key field is present in the GRE header. All these below fields are optional one. That's why they have to be mentioned whether they are present or not present, and that indication is given by these first few bits. Okay, then there is a recursion control field. Then there is a recursion control field, reserved bits, and then followed by usual fields such as version, protocol, and the optional fields. So let's see the meaning of each field one by one, and then finally we will move on to the 2784 update. Okay, so outer header, it is an IP header. As I said, the protocol type is 47, which indicates GRE, layer 4 protocol. That is protocol type of the data field is a GRE. Then source address, obviously it is a tunnel entry point, so source address will be HA address and destination address will be COA address. Okay, outer header is followed by GRE header, which uses only 4 bytes. As I said, first few 4 bits are individual bits, the first of which is a C bit. C stands for checksum. If it is present, it indicates that checksum field is available in the header. So if it is set, that means if C is equal to 1, the checksum field contains valid IP checksum of the GRE header and the payload. So checksum is calculated for GRE header plus data of a GRE header. The checksum is calculated and mentioned in the checksum field here. Okay, this is an optional field, checksum field. Then followed by R bit. C is followed by R bit. R stands for routing. Now routing information, if it is included in the GRE header, then that is indicated in the R bit. So if R bit is equal to 1, it indicates that offset and routing fields are present and contain valid information. Now what is offset? Offset represents offset in bytes for the first source routing entry. Okay, so there will be routing table entries at the router. Now offset indicates from the first entry how further is our current routing information. So if routing information is present here, then R bit indicates offset field is present. R is equal to 1 indicates offset field bit is present. So this offset field will, let's say, now in our example, this is 1, 2, 3 and 4. So in the fourth entry of a routing table, our routing information is present. That's the meaning. Okay. So how further is from the original entry? 3 entries away from the further entry. So the offset field here will contain 3. This is just an example. Now 3 means from the beginning move further 3 fields away from the first element or first entry in the routing table. Add the fourth entry, because first entry is denoted by 1, add 3 to it. That is where our routing information is present. That is the meaning of this offset field. And if it is present, it is indicated by this R bit. I hope you understood. So if R bit is present, that means offset field and routing field is present. Offset field indicates where the routing information is present, and actual routing information which is in the routing table is copied into this particular field. So routing information, that means which path to be taken to deliver a packet to the destination. Okay, so the routing field, if present, has a variable length and contains fields for source routing. Now source routing means routing information given by the source of a packet. So source routing allows sender to decide a path to be traveled towards the destination. So sender will decide how packet is traveling towards the destination, and that information is shared in the routing table, and from routing table it is copied into the GRE header, or vice versa. From GRE header it is copied into the routing table in case of reverse path. Then after C and R bit, there is a K bit. Now K stands for key. Now K bit indicates if it is present, that means key field is present in the GRE header. Now it is used for authentication. So if K bit is 1, that means key field is present, and this contains authentication information. Although it indicates that authentication information is present, how to perform authentication is not mentioned by GRE. GRE does not provide any standard for authentication. So users like a sender or a receiver can use their own authentication mechanism for making sure the packets are authenticated. Okay, so authentication algorithms are not further specified by the GRE. After K field, there is a S field. S stands for sequence number. So sequence number bit S indicates if the sequence number field is present or not. So if S is equal to 1, here capital S we are talking about, this this is the capital S. It indicates if it is 1, that means sequence number is present in the GRE header. Now sequence number helps in properly arranging the packet or combining different packets to achieve a actual data, or to combine or to form original data at the receiver. So let's see what is the meaning of S again. If the S bit is set, strict source routing is used, that is one thing. Then sequence numbers used by the decapsulator to restore the packet order. So if there are 10 packets to be received, they should be received in order 1, 2, 3, 4 up to 10. If this order is disturbed, like 1, 4, 3, 2, 5, 7, then receiver has to put them into the order. Now this is very important. If any protocol guaranteeing in order transmission is encapsulated and transferred using protocol which does not guarantee in order delivery. Okay, for example, IP does not guarantee in order delivery. IP guarantees delivery. Actually, IP does not guarantee delivery at all. Guarantee of delivery is given by TCP. So IP does not guarantee in order delivery. But if inside IP, if there is another protocol suite which guarantees in order delivery, let's say that is XYZ protocol, which guarantees all the packets will be received in order, and if it is encapsulated in IP packet, then it's the job of a receiver to put this order in place. This is out of order that will be converted in order, and that is very important because original packet was guaranteeing in order delivery, and that is achieved by this sequence number bit. So obviously sequence number bit indicates whether sequence number is present or not, and actual sequence number is mentioned in the sequence number field. Okay, so that is S bit, then followed by recursion field or recursion control field. Now this bit indicates whether multi-level encapsulation is employed or single level encapsulation is employed. This field distinguishes GRE from previous two encapsulation techniques. So encapsulation we have seen, take a one packet, put it inside another packet. So this is original first, this is second packet. I will further put it inside another packet, that is third packet. This is further put it inside fourth packet and go on, and it goes on. So this is 4-level encapsulation or 3-level encapsulation, whatever level encapsulation you want to take. So how much further these encapsulations are allowed? This is recursion. So this is denoted by recursion control field. Okay, so it represents a counter that shows the number of allowed recursive encapsulations. So if recursion control field contains 3, that means 3 recursions are allowed. One packet is entered into the other packet, that is first. The new packet is again encapsulated into the second packet, that is 2, and further in the third packet, that is 3. Okay, so this field indicates how many further encapsulations are allowed. So as soon as a packet is received at an encapsulator, in our case it will be a home agent, so it checks whether recursion control field is 0 or not. So home agent checks whether REC is 0 or not. If field is not 0, let's say if it is 2, that means home agent is allowed to do further encapsulation, which is the actual case. Home agent receives a packet with non-zero value of a recursion field. So that will be maximum 1 most of the cases. So it is allowed to do a encapsulation. Once it does the encapsulation, then it reduces or decrements this field to 0. That means it cannot be further encapsulated. If packet is received with REC field 2, it does encapsulation. The encapsulator performs encapsulation, reduces the REC field to 1 and sends the packet. Okay, so if the field is not 0, additional encapsulation is allowed, packet will be encapsulated and field is decremented by 1, as I said. So in normal circumstances, home agent receives a packet with REC field equal to 1, indicating 1 level of encapsulation is allowed. So home agent performs encapsulation, makes REC field equal to 0 and forwards the packet. Otherwise, packet will most likely be discarded. If home agent receives a packet with REC is equal to 0, then encapsulation is not possible. So this mechanism prevents indefinite recursive encapsulation, which might happen with the other schemes if tunnels are set up improperly. Okay, so improper setting up of tunnel means what? If one tunnel is leading to another another tunnel is leading to furthermore, and that furthermore is further connected to original tunnel. So let's say this is a home agent which is connected to foreign agent. Now foreign agent is also further connected to foreign agent 2, and this is connected to home agent. So in order to avoid this looping, this recursion field is important, because for every tunnel there should be an encapsulation, otherwise tunnel won't be possible, and to avoid looping, this recursion control field is very useful. The default value of this field should be 0, thus allowing only one level of encapsulation. Okay, so as I said, when HA receives a packet, it should not be 1, REC should be actually 0. Make that correction. If REC 0, one level of encapsulation is allowed. If REC is -1, it should not be allowed to perform any encapsulation. That is the meaning. Okay, 0 means default value, that means one level of encapsulation is allowed. That is the important. This is the important thing. Default value 0, allowing only one level of encapsulation. So at least 0 value should be there in the REC. It cannot be empty. If it is empty, no encapsulation can be possible. Then recursion control field is followed by reserved fields, which are 0 most of the time, but they should be kept 0 and ignored on reception. The version field contains 0 for GRE version. Then following a 2-byte protocol field represent a protocol of the packet following a GRE header. So let's recall the original format. First was a IP header, that is outer header, followed by a GRE header. Now in the GRE, it should be mentioned what is the type of a next protocol, and that is mentioned in the protocol field. So usually for mobile IP tunnel, this field contains 0 into 800 for IP. If it is Ethernet, then it contains 0 into 6558 for GRE tunnel. The standard header of the original packet follows. So after GRE, standard header follows. Let's say it is a ARP. Sometimes it may be IP also. And the source address and destination address for the inner header will be correspondent node and mobile node respectively. Okay, so that is normal, like the previous fields, previous encapsulation techniques. Okay, now this is original version of the GRE. Now this was further modified in the RFC 2784. In the RFC 2784, it does not address mutual encapsulation or multi-level encapsulation, and ignores the several protocol specific nuances on purpose. So the R field, K field, capital S field, small s field, these are ignored on purpose by the new update. Only C field is kept as it is, because checksum is useful for error detection, and C field again in the 2784 update. Let's see back the original 2784 update from the diagram. So this is 2784 update. Let's compare it. These fields are not here. So recursion control, key, routing, all are absent from this one. From version, all the fields are repetitive. Okay, so C is kept as it is. R, K, S, small s and recursion, these are removed, and since R, K, S are removed, the lower part, that is key field, sequence number field, routing field are also removed. Only checksum field is kept as it is. Okay, the second field, reserved one, is used for aligning the packet size. So these are all 0. This is fixed value. This is to make packet of a equal length. Okay, so let's see the RFC 2784 update again. Okay, C field indicates checksum is present or not. The next 5 bits are set to 0. Then 7 reserved bits follow. The version field contains value 0. This is for GRE, because GRE is used. If the C is set, checksum field and field called a reserved one follows. So if C is not set, then these two fields are also not there. Okay, so that is further reduced. So latter field is a constant and set to 0. Reserved one field is constant and set to 0. This is just for alignment purpose. To make it a 32 bit, this reserved one bit is a reserved one field is utilized. Because if you see the original diagram, then you will see that it is a 16 bit checksum is calculated. So this is a 16 bit checksum, 16 bit. These are also 16 bits. This is also 16 bit. So the upper row is of 32 bits and lower row is of 16 bit. So to make it 32 bit, further zeros are added. Okay, so that's why reserved one is there. The RFC 2784 deprecates several fields of RFC 1701, which is the original standard, but it is able to operate with the original standard. So it's not like that RFC 2784 is implemented, then you cannot implement one previous one. So it is compliant with the previous implementations also. So this is all about generic routing encapsulation, which is a final type of encapsulation in our syllabus. Now in the next session, we will see how the reverse tunneling can be implemented and what are the problems associated with the reverse tunneling. We have seen tunneling, that means from home agent to COA, tunnel exists. So reverse tunnel means in the reverse direction, how can be tunneling done. That will be for the next session. That's all for today. Thank you.